Hi guys, Mr. Ford here yet again. Today we're going to focus on series circuits. It's one of three main types, or really two main types of circuits we're going to utilize this year or analyze. Sorry. This is where you're going to learn, hopefully, um, the content that was on that quiz that we had a while back, where you didn't know anything. That we were just trying to show that you didn't know stuff that you were going to learn this year. So make sure you're paying attention in this unit. So first off, series circuits. We talked about what a circuit means. It literally means circle or a loop going around in a circular path, returning to where you came from. What about series? So where have you heard the term series? That's right, Andrew. The World Series. Why is it called the World Series? Well, yeah, it's a sequence of games, right? And one after another. Or if you just say a series of numbers, it goes one, then the next, and the next, and the next. So in a series circuit, the resistors, the things that are in that circuit, the things that are lights being turned on, if you will, they follow one another. So the current, the electrons have to go through the first and the second and the third. It's going to go through all of them. So if you take a look at this series circuit here, these little squiggly lines, just like in the analogy picture, that's the universal sign for a resistor. So this could be a light bulb or blender, or whatever we have converting that electrical energy. Here we have what looks like it's disconnected. This is the symbol for a battery. This is what's providing the voltage, that potential difference. So if the current's going to go, in this case, clockwise, it would have to go through resistor 1, then it's going to continue along resistor 2, and then back to the battery. The two sides of the battery are oppositely charged, and the electrons are going from the negative side to the positive side. So that's why it's called series, because there's only one path for the current to go through, and it goes through each resistor sequentially. Don't know if that was the right term to use, but it'll work. So with that, there's only one path. So if you were driving from point A to point B, and there's only one way to get there, and keep in mind, we're looking at wires and conductors. What are wires or conductors, other types of metals, made of? That's right, Emily. They're made of atoms. So what are atoms made up of? Good, Josh. Protons, neutrons, and electrons. So we're really only looking at the electrons flowing through from one atom to the next. So if they're backed up, or imagine our school packed with people, no room to move. Moving through the hallways, everybody's going to have to move the same speed because there's no wiggle room. So if you go faster, the people in front of you and behind you go faster. If you slow down, everybody else slows down. That's kind of how the electrons are. They're tightly packed, the atoms, and then the electrons kind of flow around through them. So in that, the current is going to be the same everywhere. Or if it was a hose and you had water moving through it, the current speed or amount of water going through is the same no matter where you are along that hose, as long as the diameter didn't necessarily change. So that's going to come in handy later on. So the rules for a series circuit, the current is the same at every resistor. Now we have to talk about resistance. So whether it's water flowing or traffic or people walking down a hallway, the more friction or more things that we put in there to resist them, it's going to increase. So the resistances are going to add. The more friction you put on something, or just within a car, just the more sources of friction, that's going to slow down that car. So to get the total, resistance is going to add. And then looking at Ohm's law, V equals IR, or I equals V over R. voltage would have to also add. Okay, so those are rules that we're going to abide by, and we're going to be utilizing Ohm's law. I equals V over R, or VIR. So we're going to complete a VERP chart. I didn't say a burp chart, Maddie. It's a VERP chart. Comes from voltage, current, resistance, power. Hence, VERP chart. So it's kind of like a puzzle, and the more you do of these, the better you get at them. Kind of like a Sudoku puzzle, or back in chem, converting units using stoichiometry. So I'm going to walk you through some. So we only have a certain pieces of information. So you just start wherever you have the most information. So we have the resistances. So there's 2 resistors, and resistance just simply adds. So we take resistor 1 plus resistor 2, so 5 plus 15 is 20. All right, so then we got to look, what can we then now find? We don't have current, we don't have power, but what is one thing that we can find? That's right, Sam. And how are you going to find it? Right, so we can find the total current right here using Ohm's law. Just so I'm not freaking people out, I do not really hear you guys. That would be kind of cool if we could do that, though. So 60 divided by 20, we're going to have 3 amps. Okay, so we have all the information for the total. And I forgot to mention, we're going to save power to the end. There's something special that works there. So what can we find? Well, we can't find voltage because we only have one variable for each resistor. But here's the trick part. Since we know the current was the same at every resistor, once we found the total resistance, or sorry, total current, that's the same current that's going to be everywhere. So I erased that. So 3 amps everywhere. So now we can find the voltage using Ohm's law again. So I times R, 3 times 5 equals 15. 3 times 15 is 45. And the main part of our VERP chart, or our VER chart, is completed. So now power. Power, we said, or if you want to look at it like this, VIP or VIP and VIR. We have our voltage, we have our current. We could just multiply and get it. So 15 times 3, we'll get our 45 watts. 45 times 3, we'll get our 135. And then 60 times 3, we'll get our 180. Here's the really, really cool part. So for most VERP charts, you can actually grade yourself. You'll know if you're mostly correct. Now, there's a little nuances. If you make a mistake here and then make the opposite mistake there, it can kind of offset. Kind of like 2 wrongs, make a right. Or 2 lefts make a right. So we found this 180 by taking 60 volts times 3 amps. Well, power is kind of like the amount of energy you're using per time, right? So if we take the 45 watts plus the 135, we actually also get 180. So this is known as the power check. If you add down your column for power, that should equal the power that you calculated doing voltage times current. Pretty cool, huh? I know. So I'm going to ask you guys to go ahead and do the series circuit 2, series circuit 3. You could see it's just increasing in the number of resistors, increasing the amount of work, not necessarily more difficult, just more tedious. So go ahead and do that on your own. Check your answers in Schoology. If you're good, you're done for the day. If not, send me a Schoology message and I'll get back to you as soon as I can.